A-Level Mechanics, Kinematics, the Work-Energy Principle. The work-energy principle relates work to energy and gives some fairly easy methods for solving mechanics problems. If work is done to a body, it gains energy, and if the body does work, then it loses energy. The energy lost or gained is equal to the work done. Now, in a complete system, energy cannot be lost, but some mechanical energy can be converted into other forms of energy, such as heat or sound. Energy can be lost by a body by means such as friction, which converts energy into heat, or a collision, which converts energy into sound and heat. It's easy to see this. If you rub your hands together, you are doing work on your hands. When you stop, all the energy seems to have disappeared, but actually your hands feel warmer. The work you've done against friction has heated up your hands. Similarly, if you clap your hands, the energy that you use to bring your hands together doesn't disappear. Your hands come to a stop, but the energy is transferred into sound and heat. We can say that the energy gained by a body is equal to the work done to the body. The energy lost by a body is equal to the work done by the body. This is called the work-energy principle. Let's look at an example. A block of mass m lies on a rough horizontal surface. Initially it has a velocity of v. The frictional force acting on it while moving is F. Find in terms of m, f and v the distance it travels before coming to rest. In part 1, solve this by using energy. So, for part 1, we'll use the work-energy principle. That means the energy lost is equal to the work done. Now the energy lost is the initial energy, a half mv squared, minus the final energy, which is naught. And that's equal to the work done, which is the force working against friction times the distance, Fd. So, a half mv squared minus naught equals Fd. If we divide both sides by F, this gives us d is equal to mv squared over 2F. Now in part 2 we're asked to solve the same problem but using Newton's laws. So the first thing to do is draw in the forces on the body. Now there's the weight, that's mg, and there's the normal reaction, we can call that r. Resolving horizontally and using F equals ma, we've got minus F equals ma. The force is in the negative direction. So this gives us A is equal to minus F over m. Now if we use the equation v squared equals u squared minus 2as, we've got the final velocity is naught, the initial velocity is v, the distance covered is d, and the acceleration is minus F over m. Substituting that in, we get naught squared equals v squared plus 2 times minus F over m times d. And that simplifies to 2fd over m equals v squared. Now if we multiply by m and divide by 2f, that gives us d equals mv squared over 2f. We get the same answer that we got when we were using the energy principle, but it's taken quite a lot longer. So we can see the work-energy principle can be used instead of using Newton's laws, and sometimes it gives a quicker and easier method to solve problems. In example 2, we're told a ramp 8 meters long makes an angle of 30 degrees with the horizontal. A block of mass m is placed at the top and released from rest. The coefficient of friction between the block and the ramp is 0.2. In part A, we're asked to calculate the velocity of the block at the bottom of the ramp. Well, to solve this, we need to draw a diagram of the block part way down the ramp and mark in the forces. The first force to mark in is the one that's always there, the weight, and that will be mg vertically downwards. Then there will be a normal reaction, which is at right angles to the slope. We can call that n. And finally, there's a frictional force which will be up the slope. We'll call it F. Now we can resolve perpendicularly to the plane. Going up we have N, and going down we have the component of the weight, mg, perpendicular to the plane. So we need the angle between the weight and the perpendicular, and that's 30 degrees. So we have N is equal to mg times the cosine of the angle between the weight and the perpendicular, so N equals mg cos 30. Now, F is the frictional force, so we can use F equals mu n. And that gives us F equals 0.2 times m times g, which is 9.8, times the cosine of 30. Or F equals 1.96 times m cos 30. Now let the final velocity be v. Using the work-energy principle, the energy lost is equal to the work done. So the initial potential energy plus kinetic energy minus the final potential energy plus kinetic energy is equal to the work done. Now the initial potential energy is mgh, which is equal to m times 9.8 times h, and h is equal to 8 sine 30. The initial kinetic energy is 0. The final potential energy is 0, and the final kinetic energy is a half mv squared. And that's equal to the work done, which is the force times distance moved, which is equal to the force 1.96 m cos 30 times the distance 8. Now the m's cancel all the way through, so we're left with a half v squared is equal to 78.4 sine 30 minus 15.68 cos 30. Well, that works out to be 25.6207. So if we double both sides, v squared is equal to 51.2414. If we take the square root of both sides, we get v is equal to 7.1583, and so we have our final velocity is 7.16 meters per second. Now in part B, we're asked to find the time taken to descend the ramp. Well, to do this, we can use the formula S equals u plus v over 2 times t. U is 0, and we've worked out that v is 7.1583. The distance travelled is 8, so 8 equals 0 plus 7.1583, all divided by 2, times t. So that can be rearranged as t equals 16 over 7.1583, which works out to be 2.235. So the time taken to descend the ramp is 2.24 seconds. In example 3, we're told a ball bearing of mass 25 grams falls from a height of 8 meters onto a block of styrofoam. In penetrating the styrofoam, it encounters a resistance of 7.6 newtons. How far does the ball bearing embed itself in the styrofoam? To solve this, draw a diagram. Let the distance the ball bearing sinks into the styrofoam be d. Now, the initial and final kinetic energies are 0, so the loss in potential energy is equal to the work done. Now the loss in potential energy is mgh, where h is the total distance that the ball bearing falls. Now the mass of the ball bearing in kilograms is 0.025 and g is 9.8. The total distance that the ball bearing falls is 8 plus d. So that's equal to the work done, which is the force times the distance. Now the ball bearing is applying a force over the distance d, so d times 7.6. Now that simplifies to 1.96 plus 0.245d equals 7.6d. And we can subtract 0.245d from both sides to get 7.355d equals 1.96. Now if we divide both sides by 7.355, we get d is equal to 0.26648, so the distance it'll travel into the styrofoam is 26.6 centimetres. Example 4. A toy called the Loop of Death consists of a model car, a flexible 2-metre length of track, a loop of track with radius 20 centimetres, and a short length of straight track. They are set up as in the diagram. The model car of mass 100 grams is released from rest at A, descends to B, goes around the loop and then runs to D. To stay on the track without falling in the loop, it must have a speed of 1.4 meters per second at the top of the loop C. The resistance running along the track is 0.24 newtons. What height must A be for the car to successfully complete the track? Well, to solve this, we need to work out the potential energy lost going from A to C. Now the potential energy is mgh. M is the mass of the car, which is 100 grams, or in kilograms that's 0.1. G is 9.8, and h is the height of A minus the height of C. Now A has height h and C has height 0.4 meters. So mgh is equal to 0.1 times 9.8 times h minus 0.4. Now let the car have speed v at C. We need to find the kinetic energy gained going from A to C. Now the car starts from rest at A, and so the initial kinetic energy is 0. And at C it has a velocity v, so it gains a kinetic energy of a half mv squared, which is a half times 0.1 times v squared. Now the work done from A to C is the force times the distance moved. Now the car is moving against the resistance, a force of 0.24, and the distance travelled is the length of the 2-metre flexible track and half the loop. Now the loop has circumference 2 pi r, so half the circumference is pi r, which is 0.2 pi. So the work done from A to C is Fd, which is equal to 0.24 times 2 plus 0.2 pi. Now the energy lost is equal to the work done. The energy lost is the potential energy lost minus the kinetic energy gained. So that's Formula 1 minus Formula 2, and that's equal to the work done, which is Formula 3. Now if we expand the brackets, we get 0.98h minus 0.392 minus 0.05 v squared equals 0.6308. Now that can be simplified to 0.98h equals 1.0228 plus 0.05 v squared, where v has to be greater or equal to 1.4. So that tells us 0.98h has to be greater or equal to 1.1408. In other words, h, the height of A, has to be greater or equal to 1.1436. So the car has to start from a height greater or equal to 1.14 meters.